Shut up! So everything's fixed. Everything's set for Thursday. We got the new practice problems are up. The new solutions are up. You're responsible for, it's like 7 practice problems total. There's 4 rigid body, 3 linkages. They're all sort of related. So really the rigid body stuff is getting you, working towards the same understanding that the linkages stuff is. So I don't feel as good about it as if we got it right the first time, but I feel pretty good about this Thursday. Okay. None. Yeah. So, but I will, so I am going to grade those tests. I don't know. So at least the ones that you already took, I'll at least give you what your scores are. Definitely if you like your score on the first one, you can keep that. Other than that, I don't know. The solution? Yeah, sure. Yeah, right. I'll do that after class today. So yeah, on Thursday we have exam 3 and exam and quiz 4. Exam 3 is on rigid body kinetics. And I think what I have them called on D2L is set number 2. And exam 4 and quiz 4 are on linkages. So we'll make sure, I think these are the 2 most important things in the class, and it's important to me that you understand these 2 topics really well. So we're focusing sort of on the fundamentals of rigid body kinetics and then linkages. And coming up, problem set 2 is due Thursday. And there's a problem with this too. When I did the solution, I overlooked something, and the way it is right now, you don't have enough information to solve it. But you do have enough information to solve it if you think of it as if you don't think of this bar being here, okay, you just think of it as a wheel rolling without slipping around this loop-de-loop. Okay, so this thing's moving with a constant speed around that ring. And you're trying to calculate the couple applied to this wheel to make it roll with a constant speed. So the arm can't be there, because if you don't know the mass of that arm, you don't have enough information to solve this. And if you include the mass of that arm, it ends up being stuff I didn't plan to put into this problem. Okay, so I'll correct that on D2L. Sorry about the hassle there. It says it's due Thursday. I mean, that's just sort of a guideline. I mean, I'd recommend getting it done as close to Thursday as you can. You can turn it in anytime up until the end of the class, which is a week from Thursday. But there is going to be one more problem set that I'm going to give you this Thursday. So you don't want to leave all the problem sets and the last topics for the last week. Any questions about that? Yes? Yeah, that's right. Well, you still know the dimensions of the big circle that it's going around, but the motion is this inner wheel rolling around the big circle, like a motorcycle going around one of those spheres of death. And so you still just have to figure out the external couple that you're applying to this wheel to make it go around. Okay, and then so that's problem set 2. There is going to be a problem set 3. Topics coming up. I'm going to finish talking about linkages today. Then what we still have to cover is, I'm going to change the order of things a little bit so that the one that's not as important will just fit into whatever time we have left. But I'm going to talk about non-inertial coordinate systems. And when we're dealing with non-inertial coordinate systems, we're going to go back to particle kinematics and particle kinetics. And then using an energy method for linkage calculations. We're not going to do this in depth. And we're not going to do the practice problems on these. So this is, you know, we'll spend a day or part of a day on this at the end, but we're going to do a good treatment of non-inertial coordinate systems. Okay. And then Monday, is the makeup exam. You can choose any one exam to do a new version of, so it's not the same exact problems you're doing again, but the same material. Any one of 1 through 4. And the quiz will be on there. You have to take the same exam and quiz, but if you're happy with your exam or you're happy with your quiz, you can just leave the other one blank and I'll grade one and take the higher and leave the other one alone and keep your old one if you're happy with it. Okay, so if you just have a bad quiz score you want to fix, you can come in for 5 minutes, take a quiz, and you're done. And nobody has to come on Monday. If you're happy enough with all your scores, you don't have to come. All we're doing is taking the test that day. Yes, I'll make sure you get your scores for the test on Thursday by the weekend. So by the end of the night Friday. And then Thursday, I think this is August 7th, I think. That's going to be the final. the topics on the final, or one topic, is going to be non-inertial coordinate systems. Well, that's the one new topic. And then also it's cumulative. So you need to familiarize yourself with those old practice problems. I mean, what I would recommend doing, going back, because probably most of you aren't going to have time to go through every single practice problem for the class again, I would recommend going back through, look at the question, and just ask yourself, do I know the steps for this? You know, like, what would I do here? If you know what you would do, if you can think like, okay, I'd first calculate this and this and this and this, then move on from that one to the next one. And when you get to one where it's not as clear to you what the steps are, then see if you can work through it. If you can't, then you need to look at that material again. But I think that's a good way to just get yourself ready for all of the material for the class. And then there's also going to be a quiz. It's cumulative. It's worth the same amount as the other quizzes. Yep.
Are you going to set it up again so like the third problem set is good review? Because I remember in statics that's how it worked out. Like when we made that problem set, it was great to go over most of the time going through it.
Huh. It's easy with statics. That's easy with statics because everything builds on itself so much. In dynamics, it's a little harder to, but that sounds like super nice. I don't remember doing that. Was that was just this summer? Oh, that's cool. Well, I'll think about that. I'll look back at the statics one. Any other questions? Okay, so let's go through a linkage problem, and then in the second half of the class, we'll start talking about non-inertial coordinate systems. Okay, so let's say that, so here's the problem. You have an isosceles triangle down here is a pin in a slot. Up here is a pin joint. Each member has a length of, let's say 3 meters, and a mass of 10 kilograms. And a force is applied to the pin here of 600 newtons. At the instant shown, this angle here, let's say that's 70 degrees. It's isosceles, so this is also 70 degrees. And let's say that what we want to calculate is the acceleration vector of the bottom pin. Okay, so like what we want to figure out is if our finger is here, is it going to hurt our finger? Okay. We already know one thing about the acceleration. We know that the x component of the acceleration is 0 because that pin can only slide along that vertical slot. All right, so let's start out by numbering the members. I'll call this 1, this 2, And for joints, I'll call this A, B, and C. And so the steps that we're going to take are one by one. We're going to go through all the members, treat it as a rigid body problem, find the equations of motion, Newton's laws for it. At the end, we're going to figure out how many equations we have, how many variables, use that to figure out how many constraint equations we need, and then come up with the constraint equations and solve this big system. So this is going back to statics. This 600 Newton force is acting on the pin. We're going to lump that in with one of the two members. How do we choose what member? Yeah, let's go to the lowest numbered member. So we're going to treat that 600 Newton force like it's acting on member 1, but not on member 2. All right, so member 1. So when you're dealing with a rigid body, you have to think first, is there a fixed point or is our about point going to be the center of mass? So what's the deal with this one? Yep, it's fixed at B. So that's the about point. And so now we can calculate the moment of inertia. So the moment of inertia about B is equal to, we're treating these like slender rods. We don't know the thickness. And so the moment of inertia is 1/12 times the mass times the length squared. That's the moment of inertia about the center of mass. Now we have to use the parallel axis theorem. So the mass is 10. What's the distance from the center of mass to the point B? 1.5. So can someone calculate that?
So we're doing the center of mass that we're using for the parallel axis theorem is the center of mass for each individual.
Yes, just for that body. Yep. 30? Ooh, that's convenient. Kilogram meters squared. So now free body diagram. So what are the forces? Well, we have the weight. At the pin with the ground, we have a force vector. So that's the force on one by the ground. What do we have at A? We have the 600. Anything else? Yep, we also have the force on 1 by 2. And that's complete, so write out the table. Pancake, artist, row, 4, marzipan. We have to choose a coordinate system. I guess this isn't a bad one. So what's the angle from the positive x-axis up to this bar? 20, yep. So, okay, well, first, if we do the 600 and F12, the location of those is the origin. What's the about point? Or how do we find that? That's that point B right here. So yeah, that's 3 times cosine of 20, 3 times sine of 20. So what's that?
1.22 for cosine. And 2.73.
You might be in radians. Okay, 2.81. Okay, and the second one?
1.026.
Okay, 1.03. Okay, so the row vector is negative 2.81, negative 1.03. Force vector, so first I'll do the 600. So what do you get when you take that cross product? Positive 1.03 times 600. Okay, and that's a z component for when we, if we ever need that as a vector. And now the F12, that's also at the origin. The about point stays the same for all of these, so we get the same row vector. So we get negative 2.81 F12y plus 1.03 F12x. And now the weight force, where's that? Halfway, yep. So it's going to be half of this, so negative 1.40 or 41, and negative 0.52. Oh, those are both positive, yeah. I guess that's more like 1. The about point is still 2.81, 1.03. And so the row vector is negative 1.41, negative 0.51. The force vector is 0, negative 98.1. So what's 1.41 times 98.1? Okay, and then there's one more. That's the force of the pin. Since it's acting, I mean, this is acting at the about point, so these are going to cancel. You're going to get 0 row vector. The force is F1gx, F1gy, and you get no moment. Any questions about anything on there? All right, this has a fixed point, so do we need Newton's second law? Nope. So the rotational equation says 618 plus 138.3 plus 1.03 F12x minus 2.81 F12y is equal to 30 times alpha 1. So I'll rearrange this. We get our first useful equation. It says 1.03 F12x minus 2.81 F12y minus 30 alpha 1 is equal to, what do you get here? 756.3 negative. So we have one equation. And for variables, how many variables do we have? Yeah, just 3. What about f1g, x, and y? Yeah, they don't matter. They're not in our set of equations. So we have f12x, f12y, and alpha 1. So 3 variables. And now go to the second body. Does member 2 have a fixed point? Nope. Even though there's a pin here, that pin can move. And this isn't fixed. It can slide along that point up and down, that slot up and down. So we have no fixed point. So the about point is the center of mass. The moment of inertia about the center of mass is 1/12 times the mass times the length squared. So what do you get there? $7.5. So now free body diagram. What forces are acting on this? Yep. Okay, so up here, there's the force on 2 by 1. That's equal to the negative force on 1 by 2. There's the weight, 98.1. And what kind of force do we have at the pin in the slot? It's horizontal. It's perpendicular to that slot. So that just has a single scalar variable associated with it. I'll call it R. So write out the table. So the force negative F12, that's at our origin. For linkages, I don't know. Yes. Okay, yeah. The 600 can only act on one of those two members. No, if you put it on both of those two members, it would have the effect of having an external load of 1200 newtons. So you have to just choose one or the other. And the way we always did it in statics was do the lowest numbered member, just so you can keep track of it. I suppose it would be, yeah. That would be an odd thing to do. But yeah, I mean, that would be basically like the pin being split in half between the two of them, yeah. Yeah, the lowest numbered member. You could treat the pin totally separately, but you just end up with a ton more equations and it doesn't help you find anything that we want. So we tend to just lump the pin in with something. Yep, that's right. And 2 more equations every time you did that. Any other questions? Yep. That's just what I was trying to draw here. Oh, so it's perpendicular, so it could be left or right. And with a pin in a slot, it doesn't, I mean, you might be able to have intuition about that in a lot of cases. Like in this case, we know from thinking about what's going to happen that that slot's going to be pushing on the pin this way, you know? But it doesn't matter. You don't have to have any intuition. Just pick one of the two directions. And you'll come out with a positive or a negative answer, which tells you whether your default direction was right or wrong. And even then, you don't care. You know, you just plug it back into your vector and it gives you the right force vector. So the force negative F12 is at the origin. Oh, I was going to say, when I'm doing linkages, I'm in the habit of just always keeping the origin in the same place, but you can move it around. Every rigid body, you could choose a different origin. What you can't do is change the orientation, because then you'd be adding components of vectors that actually mean different things, you know? But if you wanted to, for this rigid body, move the origin down to where that R is acting, that'd be fine. Okay, so what's the about point?
It would be at the center of mass.
Mhm. Yeah, and so that's 1.41 negative 0.51. Right, this angle is negative 20. So it's 1.5 times cosine of negative 20, 1.5 times sine of negative 20. So the row vector is negative 1.41, positive 0.51. The force is negative F12x, negative F12y. And so the moment is 1.41 F12y minus 0.51 F12x. Oh, wait, I just overlooked that negative. So this should be positive. Yeah. And now where the weight is applied, well, that weight we're applying at the center of mass. So there's going to be no row vector. Of course, you know, you could enter those values in and calculate that. It would come out, but the force vector is 0, negative 98.1. So there's no moment. And then the last one is this horizontal force from the slot. That's at the location 2.81, negative 1.03. Our about point is 1.41, negative 0.51. Subtract and you get 1.41, negative 0.51. The force vector is negative R0. And so you get negative 0.51 R. This doesn't have a fixed point, so we have to use Newton's second law. Because when we're expressing accelerations later of points, we're going to have to use the relative motion equation. And so we're going to have the acceleration of the center of mass as one of our variables.
Okay, so this is just
Looking forward, yeah. So Newton's second law says negative F12x, negative F12y, plus 0, negative 98.1, plus negative R0 is equal to 10 times the acceleration. So a center of mass 2 x and y components and then the rotational equation says 0.51 f12x plus 1.41 f12y minus 0.51 r is equal to the moment of inertia, 7.5, times alpha 2, the angular acceleration of body 2. So this gives us, some new variables. Yeah, so so this is, I'll call this equation 2. From body 1 we had, question? The first member has a fixed point, and so anytime your member has a fixed point, you don't have to use Newton's second law. You might need it later, but most of the time you don't. If you need it later, you can go back and get it, But the reason you don't need it is it's like the flip side of what you were just asking, Brian. It's like if we want to calculate the acceleration of any point here on this member, we don't need to use the relative motion equation because we have a point that we know has 0 acceleration. So it'll work fine without knowing the acceleration of the center of mass. Okay, so the second equation says negative f12x minus r minus 10a center of mass 2x is equal to 0. Equation 3 says negative f12y minus 10a center of mass 2y is equal to 98.1. And equation 4 says 0.51 f12x plus 1.41 f12y minus 0.51 r minus 7.5 alpha 2 is equal to 0. So now we have 4 equations. Our variables from before are f12 and alpha 1. So f12x, f12y, alpha 1. And now we got some new variables from these equations. R.
Is alpha 2 the same as alpha 1, or is it a new variable?
Those are,
Or do we just...
we're going to assume, those are new variables. Okay. Because of the geometry of this problem, they're going to come out to be equal and opposite. Okay. Like if you notice that you can't make that triangle non-isosceles, right? That angle has to be the same for both of them. And so, so their angular position is always equal and opposite. So if you took whatever the function is for angular position, if you took the time derivative, the angular velocities have to be equal and opposite. Take another time derivative, angular accelerations have to be equal and opposite. But we're not going to mess with that. That'll come out in the math. Okay. So yeah, to us, they're different variables. You could use that. The one that we're going to use is, that ends up being the equivalent constraint, is we're going to say that the x component of the acceleration of that point C is 0. And it's cool, like there's nothing right off the top of your head that would make those constraints identical. But when you add up all these equations together, that's the effect that it has. And if you just think physically about what's going on, like both of those are saying this is an equilateral triangle. You could say it either of those two ways. Okay, so we got F12, alpha 1, R. What else do we have? A, COM, 2x, A, COM, 2y, and alpha 2. So we have 4 equations, 7 variables. So we need 3 constraint equations. And here's another thing that is kind of cool the way it works out. And this isn't a coincidence in this case. It always works out like this. Like in the other example we did, we needed an even number of constraint equations. That was because the constraints that we had in our problem were 2-dimensional acceleration constraints saying the accelerations meet at a point. You know, the accelerations have to be the same where the 2 members are connected. In this case, we have 1 constraint like that. We're going to get 2 equations from the constraint at this point A, and we're going to get we need 1 more constraint equation, not 2, and we're going to get that 1 from an equation saying no x component of acceleration here. So what you need kind of pops out of the geometry of the problem. All right, so we need 3 constraint equations. Two of these are going to come from saying that the acceleration at A according to member 1 is equal to the acceleration at A according to member 2. And then we're going to get the last constraint equation by saying that the acceleration at C, or not the vector, but the x component of the acceleration at C is equal to 0. That's because that pin in the slot can't move side to side. It can only slide up and down in the slot. All right, so the constraint at A. So let's do it first according to member 1. How are we going to represent the acceleration? How are we going to represent the acceleration of A according to member 1? Yeah, we need that watermelon equation. We don't need relative motion because this is actually in a pure circular motion about the fixed point B. Okay, so
I thought the watermelon equation is just when you're relating a particle's motion to the center of mass.
Not just the center of mass, any point.
Okay.
Yeah, so it's so when you're treating a rigid body as rotating around any point, whether it's the center of mass or a fixed point, you use that equation. So the acceleration at A is equal to the angular acceleration of member 1 crossed with the r vector. And what's the r vector that we want? Going to what from what?
From A to the point.
It's going from the center of your rotation to the point that you care about. So it's to A from B. Okay, so I'm going to write that as R to A from B. And then the angular velocity. Did I say they were angular velocities?
No.
Did I say anything about it? No. I should have. Let's say that there's not, though. It'll just make the calculation a little easier. What? If there's no angular velocity, then it's at rest at that instant. So it can have acceleration but no angular velocity. So at this instant, the angular velocity of member 1 is equal to the angular velocity of member 2, which is equal to 0. Like I said before, because of the restrictions on this isosceles triangle, these would have to be equal and opposite. So I could specify any angular velocities, you know, as long as one's positive and one's negative. Okay, so omega cross omega 1 cross RAB. This all goes away because there's no angular velocity. And so we have 0, 0, alpha 1 crossed with, numerically, what's that vector from B to A? Yep. So negative 2.81, negative 1.03, was it? 0. So the x coordinate, you get positive 1.03 alpha 1. The y coordinate, you get negative 2.81 alpha 1. That's according to member 1, and now we're going on to the acceleration at A according to member 2. So according to member 2, the acceleration at A is a little more complicated now because there's no fixed point. So the acceleration at A relative to the ground is equal to the acceleration at A relative to the center of mass plus the acceleration of the center of mass relative to the ground. This one comes from the watermelon equation. And this one is just a fancy name of saying ACOM2. So the acceleration of A is equal to, so I'm going to write out the watermelon equation and then just add ACOM2 onto the end. So we have the angular acceleration of member 2 crossed with the r vector from what point to what point? Yeah, 2A from the center of mass. Yep. So R 2A from the center of mass. plus omega 2 cross omega 2 cross RACOM. I guess really I should write this as COM2. This whole thing goes away. And then the relative motion equation says don't forget to add on ACOM2. So you get 0, 0, alpha 2 crossed with, what is this numerically, this vector 2a from the center of mass of 2? Negative 1.41, negative 0.5, or positive 0.51. Zero plus a COM 2 x and y take this cross product and you get minus 0.51 alpha 2 as the x component. The y component, you get negative 1.41 alpha 2 So the constraint equation then says this is equal to this. So now I'm going to rewrite, what are we on? We have 4 equations. So these are equations 5 and 6. Equation 5 says 1.03 alpha 1 plus 0.51 alpha 2 minus a COM2x is equal to 0. Equation 6 says negative 2.81 alpha 1 plus 1.41 alpha 2 minus a COM2y is equal to 0. So now we have 6 equations, 7 variables. So we have to use that one more constraint equation. So now we have the constraint equation at C to do. So how do I want to represent the acceleration of that point C? What? Yeah, right. So, but that would be another variable. So we want to do it in terms of the variables we have, which are the acceleration of the center of mass of 2, the angular acceleration of body 2. So we're going to use the relative motion equation to say, you know, the acceleration So first, let's just come up with an expression for the acceleration of the point C. Okay, so AC relative to the ground is equal to the acceleration of C relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. This one comes from the watermelon equation. This one is just a new way of saying ACOM2. So A acceleration of the point C is equal to alpha 2 cross, what's our R vector that we want? From what to what?
From C, from center of mass.
Yep,
C.
that's right. From the center of mass to C. So we want the vector to the point C from the center of mass of 2 plus this, which is all going away, and then plus the acceleration of the center of mass of 2. So that's 0, 0, alpha 2 crossed with, what's the vector 2c from center of mass of 2? Negative of that. So positive 1.41, negative 0.51. It's just, we're just looking for a vector going from here to here. Oops. 1.41, negative 0.51, 0, plus a center of mass 2. This cross product has an x component of 0.51 alpha 2, a y component of 1.41 alpha 2, and then add on the center of mass of 2. And we know that this has to equal 0, and then don't care. So we're just going to separate out the x component of this equation. So equation 7 says 0.51 alpha 2 plus a COM2x is equal to 0. Then we'd have nine variables and 8 equations, because we'd have, like you're talking about using both components, right? Because you'd also have, oh. So this would be your last one. Yes, you could do that. Yep.
Is there a reason why we didn't use the second?
Because we don't know anything about the y acceleration. It can slide, this can slide at any value of acceleration up and down that slot. All we know is that there can't be any acceleration perpendicular to the slot. That's what that slot does. That's the motion it restricts. Okay. Let's take a break, and I'll set up this matrix and we'll look at the answer. Okay, so come back at 2:12.